Lecture 2, The Night Sky. This covers chapters 0 and 1 in your textbook. In order to begin discussing the night sky, we need to use numbers. And astronomers have found that the universe is very large, as we discussed in Lecture 1. As such, we often are dealing with very large numbers, and we use different tools to make those numbers easier to handle. One of the tools we use is scientific notation, which allows us to write numbers more compactly, as you can see here in the chart on the left-hand side. And astronomers also make use of somewhat non-standard units, such as the light year and the astronomical unit. The astronomical unit, or AU, is a unit that is defined as being the distance between the Sun and the Earth on average, which is about 93 million miles. But even that is not a big enough measure if you're trying to talk about the distance between stars. In that case, we tend to use something called the light year, which is defined as the distance that light can travel in 1 year, which turns out to be about 6 trillion miles. Even with such a large distance unit, it's still 4.1 light years before we can get to the nearest star. Even the Earth seems relatively large when you think about our everyday use of units. Of course, it's not large in relation to the universe, but based on things like tons and kilometers, you can see by the numbers here that it quickly becomes unwieldy to try and write out all of the zeros required to express those values. And again, this is another example of why we use scientific notation to make our numbers more compact. Now, ever since a long time ago, people have wondered about the shape of the Earth, and it's been debated in different societies whether the Earth was flat or round, etc. But even in Aristotle's time, there was reason to look around you and deduce that the shape of the Earth is indeed round. Aristotle reasoned that during a lunar eclipse, the Earth's shadow produces a curved shadow on the moon. The moon itself is round, as is quite obvious during a full moon, and when that shadow occurs, it's also an arc, which seems to imply that it comes from a circular shadow, which would be produced by a round object. In addition, Aristotle noted that, well, some stars are visible in the northern hemisphere, but not visible during the southern hemisphere. And if the Earth were flat, it's hard to imagine how that could possibly be the case. So even from ancient times, people like Aristotle were able to deduce that the Earth was in fact round. The moon, as I said earlier, is obviously round. When you see it, you see that it's grayish in color. It seems to have been hit by a lot of things. There are lots of craters, sometimes craters within craters. You might ask yourself then, why do we have so few craters here on Earth? And there are a couple reasons for that, but the biggest of which is that here on Earth we have weathering processes and geological processes and biological processes that the moon does not have. So if we're struck by something and it rains and it erodes the crater, or a volcano happens and lava gets spewed on top of it, or an earthquake, or even vegetation growing on top of it, then that crater is going to be effectively erased. Whereas on the moon, you don't have these things, and so these craters are basically preserved almost as though they had just happened. But again, ancient peoples wondered, well, what about the moon? Can I tell anything about how big it is compared to the Earth? And, maybe how far away it is. Aristarchus, who was also back in ancient times, tried to reason his way through this, again using the shadow that occurred during a lunar eclipse. And based upon this, he was able to estimate that he thought the moon was about 1/3 as large as the Earth, and that it was about 70 Earth radii away, meaning take the radius of the Earth and multiply by 70, and that's how distant he felt that the moon was away. Turns out that these numbers are not too far off. Instead of being about a third as big as the Earth, the Moon is more like 27% of the size of the Earth, and instead of being located around 70 radii away, it's 60 Earth radii away. Nevertheless, this is a pretty good estimate given that you're just looking at the shadow and trying to deduce the geometry from there. Even more remarkable, in my opinion, is the estimate that Eratosthenes came up with, where he wanted to know the circumference of the Earth. And he did this remarkably without actually going anywhere. He knew that at a certain time of year, namely the summer solstice at noon, there was a well in the town of Syene where the sun would shine directly overhead and illuminate the water deep within the well. And so that must mean that at that point, the sun rays were making a perpendicular angle with the surface of the Earth. It was directly overhead. We're near the equator, and it makes sense that that would be the case. But he also knew that where he was located in Alexandria, you never had quite that phenomenon take place. There were no wells in Alexandria where the deep water would be illuminated because of the sun being exactly overhead. It was close to overhead, but not quite exactly. So Eratosthenes stuck a stick in the ground and said, okay, well, on the summer solstice, I'm going to measure what angle this makes with the sunshine. And he did that and found the angle to be about 7 degrees. So how did this help him measure the circumference of the Earth? Well, if you know the distance between that stick and the well, which he did, then you can say to yourself, okay, well that distance represents 7 degrees of an entire circle of 360 degrees. So, if that's the fraction, I can figure out how many miles or how many kilometers or whatever unit they were using back then it is for 1 degree, and then just multiply that by 360 degrees. And bam, I've got the circumference of the Earth. And so based upon that, he estimated that the circumference of the Earth, he estimated that its diameter was actually 13,000 kilometers, which is just about right. Okay. Once you have the circumference, we know that 2 pi r, or pi times the diameter, is what the diameter is equal to. So, you've got the circumference and you can work out the diameter. And his estimate was actually very accurate, which is remarkable again because he didn't go anywhere. He just stuck a stick in the ground and was able to deduce these things. Another very obvious object in our sky is the sun. It is the closest star to the Earth, so that's kind of a trick question. Sometimes people say, where's the closest star to us? And everyone says Alpha Centauri or Proxima Centauri, but actually it's the sun. We don't think about it that way sometimes, but the sun is indeed a star. The sun is about halfway through its lifespan, so it's expected to have a lifespan of about 10 billion years altogether, and we're about 4.5 billion years into that. It's immense compared to the size of the Earth. You can see in the picture here the Earth and sun shown not obviously distance-wise to scale, but size-wise to scale. If you were to dump Earths inside the volume of the sun, you could fit 1 million Earths inside of it, just to give you an idea of how much bigger we're talking. And so naturally, with this being an obvious object in the sky, people wondered again, can we deduce anything about the size and distance of the sun, just the same way we were doing with the moon? And Aristarchus set about doing that and came up with some estimates. They weren't as accurate as some of the other estimates that he came up with, but he's basing these things on triangulation and trying to get a handle on these angles that precisely is tricky. But the point of it is that he set about using the tools that were available to him, namely his eyes and angle measures, to figure out things about distant objects out in space. And that is really the whole crux of astronomy, because there are very few things that we've physically been able to go to or send robots to. And so oftentimes we just have to use what we can see and what tools we have available to us to probe what's out there in space. Okay, so our solar system now, we know that it consists of a lot of things. In ancient times, there were some of the planets that were visible to the naked eye, namely Mercury, Venus, Mars, Jupiter, and Saturn. You could see as twinkling objects, and so they didn't really know that they were worlds like we know them today, but they were obvious to the naked eye ever since the advent of humanity. So now we know that those are just a few of all the planets that are in our solar system. We also have ones that are not visible to the naked eye. We have dwarf planets, we have comets, and we have asteroids as well. In addition, there are also moons that orbit planets. And so all of these things that orbit the sun are generically referred to as the solar system. Okay, so another thing that you can do when you're looking up at the night sky is you can determine size and distance, not really in absolute terms, but how much of an angle something takes up. This gives you a sense of the size and distance of objects in relation to how we see them, at least. How you do this is, if you look at the figure to the left, imagine if you were standing at the center of a great circle. And that great circle goes up overhead and down below and completes 360 degrees. And so when you're looking at some object, you may ask yourself, well, how much angle of that whole 360 degrees does it take up? For example, the moon here would take up half a degree, whereas the distance to the two stars on the right here would be 5 degrees. Okay, so we can call that angular size or angular distance. Again, it doesn't really tell us anything about the actual physical distance, but it will help us navigate the night sky. Another tool to help us navigate the night sky are constellations. Of course, there were often legends that went behind these constellations, and really it's funny because they're only just tricks of the eye when you think about it. Of course, in ancient times, people didn't know this, and they had a spectacular night sky to look at, free of light pollution, and also a lack of other sources of entertainment. And so, it was natural to kind of connect the dots and imagine figures or shapes in the night sky. But in actuality, most often, these stars are nowhere near each other in physical space. For example, we have the constellation Orion here, and in the top two pictures, you see, what you might see if you just looked up at the night sky and what you might imagine if you were an ancient person imagining this person Orion in the night sky. But in the bottom left, you see that these stars are actually very distant from one another in space. They just sort of project onto what appears to be close proximity to our eyes. So looking at the bottom right here, it's as if they're projected onto some screen, even though they're very different distances away from us. But we can take this concept of imagining stars to be on this surface of a screen, and then imagine that that screen encompassed the entire Earth. It would be like being in a planetarium then, and you're seeing all the stars projected on the inside of the dome. Now we know in reality that they're not actually at the distance of the dome, and that's just in our minds, but we can use that as a tool to help us navigate the night sky. This model or tool is called the celestial sphere. And with this, we take the distance to the stars out of the equation. Now we only need to worry about, well, how far north do I need to point my telescope? How far east-west do I need to point my eyes or direct my attention in order to find my way through the constellations or to the star, whatever object I'm interested in looking at. So in this case, there's no physical sphere that surrounds the Earth. There's no real sphere. It's imaginary, right? But it doesn't really matter if all you're concerned with is how far north do I look, how far west, how far east. That's all that really matters if you're trying to navigate your way around the night sky. You don't care that one star is so many light years away and another star is 52 more times light years away than that one. You just care how close is it apparently. How much do I need to move my telescope to see that star? Okay, and so with this construct of an imaginary sphere surrounding the Earth that we call the celestial sphere, then you can talk about where the stars are located on the celestial sphere. Are they close to the north celestial pole? Are they near what we would call the ecliptic or the celestial equator? And you can find your way around the night sky that way. But of course, the night sky doesn't stay the same. Depending on the season of the Earth and the time of the year, then you're going to see different constellations and different stars being prominent in the night sky. In the upper left here might be a view that you would see in the summertime in the northern hemisphere, whereas during other times of the year you may see different constellations if you're looking that same direction. And you can navigate from one constellation to another. The middle picture in the top here is showing you how you can find your way if you found the Big Dipper to the North Star Polaris. But the point is that this view is always going to be changing, especially if you're looking in certain directions. And you're probably familiar with this term zodiac. The zodiac, as astrologers use it, has to do with some idea of how these stars could possibly influence your life. And there's really no scientific reason to think that that could be possible. There's no evidence to support that. But nonetheless, the constellations that you may be familiar from hearing in terms of astrology, such as Leo or Sagittarius or Capricorn, really do change throughout the year, and different constellations become more prominent during different times of the year. So astronomers use that term when they're talking about, they may use zodiac, they may use, some sign of the zodiac, such as Libra, to discuss constellations. But in terms of science, astronomers do not believe that the stars influence your life. That is solidly in the realm of pseudoscience. Because there's no evidence to support that claim, and there's no means by which there's any way that we could possibly see a scientific reason for that. So astronomy is really just talking about where things are and what the phenomenon are that we have evidence to support, whereas astrology, it supposes that somehow there's something that we can't explain that's influencing you, but there's really no reason to suspect that that's the case. Another thing that's going to change your stars throughout time and what you see in the night sky is a phenomenon known as precession. Now, precession occurs because the Earth, while it's spinning, its axis is not always pointing in the same direction. It's kind of as if you had a spinning top, and once it's been spinning for a while, it starts to apparently wobble as it's spinning. And this is what's happening with the Earth. It's not always pointing in the same direction. So what that means is that different stars are prominent in the North Pole at different times if you're looking up towards the North Pole. Right now we've got Polaris, but in ancient times it was a star called Thuban, and thousands of years from now it may be Vega. Incidentally, there's a common misconception that the North Star Polaris is the brightest star in the night sky, but it's actually not that bright. Vega would be a lot brighter if that's the epoch in which we were, but for now, Polaris happens to align with celestial north, and that's why we call it the North Star. But that changes throughout time. Another thing that our axis is responsible for is producing the seasons we experience. So a common misconception is that when we have summer, it's because the Earth is closer to the sun. But if that were the case, then everywhere across the globe would experience summer at the same time. And you may already be aware that when it's summertime here in the northern hemisphere, it's actually wintertime in the southern hemisphere. So if it was because of the Earth being closer, then the southern hemisphere would not have winter, it would also have summer. Thus, a different mechanism must be responsible for our seasons, and that turns out to be our tilt, the tilt of our axis. And what that does is it makes it so that in some times of the year, part of the Earth is leaning in towards the sun, while another part of the Earth is leaning away from the sun. And this may not seem like a big deal, especially, because that distance doesn't seem like it would be significant in the scheme of things, and it's not. However, when you're leaning in towards the sun, you're receiving more direct sunlight and longer hours of sunlight than when you're leaning away from the sun. And so let's start in the left here with June. And you see, as pictured here, the northern hemisphere is leaning in towards the sun, and that's consequently meaning that the southern hemisphere is leaning away from the sun. So here in the northern hemisphere, we're receiving more direct sunlight and longer daylight hours, which gives us the warmth of summer. In the southern hemisphere, it's just the opposite. They're leaning away from the sun, so the sunlight they're receiving is more indirect, and they have fewer hours of daylight, and so they're experiencing cooler temperatures. They're experiencing winter. If you imagine going then to the bottom of the picture here where it says September, now neither the northern hemisphere nor the southern hemisphere are leaning in towards the sun or away from the sun. And so both hemispheres are experiencing moderate temperatures. And so this is producing fall for us, or spring for the southern hemisphere. We have fall because we just had summer, whereas the southern hemisphere has spring because they just had winter. Then going over to the right, we're continuing on counterclockwise here. Now it's December, and we have the opposite scenario that we had in June, where we're leaning away from the sun, whereas the southern hemisphere is leaning towards the sun. So we're experiencing more indirect sunlight and fewer hours of sunlight, whereas the southern hemisphere is experiencing more direct sunlight and more hours of sunlight. Thus, they're experiencing summer, whereas we're experiencing winter. Then continuing on counterclockwise to March, you see again we have a similar situation to what we had in September, where we're neither leaning in towards the sun nor away from the sun, so we're all experiencing moderate temperatures, but we call it spring because we just came from winter, whereas the southern hemisphere is calling this fall because they just came from summer. Okay, and so another thing you may have noticed looking up in the sky is that the moon is not always looking the same. Sometimes it looks like it's fully illuminated, and other times it looks like it's only half illuminated or a tiny sliver of it illuminated, and this is known as the phases of the moon. People also seem to think that the phases of the moon influence your life. You may hear people say, oh, my kids are acting so crazy because it's a full moon. But again, we know of no mechanism by which that would influence your life, so rest assured you're not going to be influenced by the phase of the moon. Nonetheless, it's helpful to understand what's happening here. A common misconception is that the far side of the moon is also known as the dark side of the moon. In other words, it's in perpetual darkness. But in actuality, that's not the case. If you start at, say, again, we'll imagine this being a clock. So look at where 3 o'clock would be, and you see that the back side of the moon is in full sunshine. So it's clearly not dark at this point. However, to us, it appears dark, because from our perspective, all that sunshine is on the far side of the moon. We see none of it illuminated, and so we call this phase a new moon. If we proceed on to the waxing crescent, which would be, I don't know, around 1 o'clock or something, 1 or 2 o'clock, you see that now we can see part of the moon being illuminated. And then if we move our way up to, say, noon here, we see about half of it being illuminated. This is confusingly called the first quarter because it's a quarter of the way around its whole cycle. But really, during the first quarter, it isn't a quarter moon that we see. In other words, we see half of it illuminated, not a quarter of it illuminated. Moving on to the waxing gibbous, now we're seeing most of the moon illuminated. Now you may wonder, why did we call this waxing crescent and waxing gibbous? What's this waxing effect? Waxing is just a fancy way of saying it's becoming more illuminated with each night. Okay, instead of becoming less illuminated as the nights go on, it's becoming more illuminated. And as we proceed on, you'll see what the opposite of that is. After the waxing gibbous, right around 9 o'clock there, you see the full moon. Now all of the full sunshine we see being reflected off the moon. And we can continue on to the waning gibbous. And this is where most of it is still illuminated, but it's waning, meaning that it's becoming less illuminated each night. Moving on further, you see the third quarter moon, where we see half of it being illuminated, and then the waxing crescent, where only a small portion of it is illuminated, and it's continuing to become dimmer and dimmer, less of it illuminated from our perspective each night. Now, I shouldn't say that less of it is illuminated. It's really less of it illuminated as seen by Earth. If you look at the smaller images that are, look like they're on the circle that's drawn of the moon's orbit, you see that at all times, some half of the moon is always illuminated. But it's just that to us, we can only see the part that is facing us. And so more or less of it will be illuminated to our perspective, but in actuality, all of it is illuminated at all points in time. Half of it is illuminated. Okay, another thing that can occur is that if the alignment is just right, we can either block out the sunlight to the moon or vice versa. If the moon blocks out the sunlight to us here on Earth, we call that a lunar eclipse. A solar eclipse. And what happens is that basically the moon gets directly in the way of the sun and produces a shadow on the surface of the Earth. And so you can see here that you see that happening both in a cartoon and then also a picture of the Earth. You see the shadow, and you see that not all of the Earth is in shadow, right? It's only just the portion that aligns that way. And if you were to look at that solar eclipse, the bottom right is what you would see. However, you really never should look directly at a solar eclipse because that could cause eye damage. There is a solar eclipse taking place here in August, and it's not going to be very visible here in western Pennsylvania. However, if you travel to, say, Kentucky or Tennessee, you should be able to see it pretty well there. But again, you want to look at it indirectly if you get that opportunity. Okay. The opposite scenario is a lunar eclipse where the sunlight is being blocked from the moon by us, the Earth. So during a lunar eclipse, then what's happening is we're producing a shadow onto the moon. Now, when the moon produced a shadow onto us, it was kind of boring. It was just a dark patch. And that's because there's nothing special surrounding the moon. However, surrounding the Earth, we have an atmosphere that light can get through, right? Obviously, light can't get through the solid Earth, but it can get through the atmosphere. And so some of the sunlight skims the atmosphere and is then projected onto the moon. And then the reason that it's this reddish color, sometimes you may have heard people call it a blood moon. I'm sure you've seen this because this phenomenon is actually much more common than a solar eclipse. But the reason that it's reddish in color is sort of the same reason, similar reason to why it's reddish in color during a sunset or a sunrise, and that's because the sun rays have to go through a large portion of the atmosphere when the sun is low on the horizon, and that's essentially what's happening here. It's going through a lot of the Earth's atmosphere, producing a reddish hue that's then projected onto the moon. So the question might be then, why do we not get an eclipse every month? Why is it that during every new moon it doesn't block out the sunlight to us, and why don't we block out the sunlight every full moon? And the reason for that is that the moon's plane of orbit is sort of tipped in comparison to the Earth's orbit around the sun. And so it's not always possible for that shadow to be projected onto the other object. And so the cartoons here are trying to show you, different situations in which you could or could not have an eclipse. So I designed these PowerPoints for an in-class session where we could use clickers, but this is a good sort of mental test for you to think about. You obviously can't click anything, but imagine, see if you can answer this question. Why is it cold in the winter and hot in the summer? I'll give you a minute before I move on to the next slide. And hopefully you chose C because we discussed at length how it's due to the Earth's orbital tilt, tilt of its axis, not its actual position in its orbit. Another question for you is when the moon is located between the Earth and the sun, what kind of phase would that be? So try to picture it for a moment. Maybe you want to sketch it out. Okay, and hopefully you answered that it was a new moon phase, right, where the backside of the sun is being illuminated, so we don't see that from our perspective. Another question for you, if you see the arrangement below, what could it correspond to? The yellow is the sun, the blue is the Earth, the gray is the moon. And the correct answer here is that this would correspond to a full moon, so it's the opposite scenario as when the moon is between the Earth and the sun. And the reason that it's not producing a lunar eclipse is because you see how the orbital planes are not aligned in such a way that the Earth could produce a shadow onto the moon. Got to have just the right alignment for that to occur. Okay, so how do scientists know all these things? I've given you a little glimpse into how, ancient peoples tried to reason through things and figure things out. But, what of astronomy as a scientific field? How is it that we really understand and are sure that we know these things? So, you've probably discussed the scientific method in other classes, so I don't want to dwell on this. But it's good to serve as a review and underscore the importance of the scientific method in terms of how it serves as a tool for us to understand the universe around us. So scientific method usually starts out with some kind of hypothesis. It's important that that hypothesis be testable. It's surprising how many people don't know what testable means. It just means that it's able to be tested. If you say the sun is some magical god that you can never learn anything about, then you can't really call that a hypothesis because you can't really test it. Okay, and hopefully that's given you some time to sort of look over these other concepts in the scientific method. There's the concept of a theory and a law. A common misconception is that a theory will eventually become a law once it's quote-unquote proven. First of all, nothing is ever completely proven. There's never a shut case where we carve something in stone and never revisit it again. Both theories and laws are always subject to revision. And secondly, theory is just as sure a thing as a law. It's just that they answer different questions. That's why we have two different categories. A theory really just answers, or a law, let's start with a law. A law answers how something takes place. So if I talk about the universal law of gravity, then I'm telling you that the force between two massive objects is equal to gmm over r squared. I can, summarize it with an equation and say it very succinctly, but I'm not telling you why those two objects behave the way they do. That's what we need a theory for. A theory is answering the question why. Why is there this force between these two objects? And that's why we need the theory of gravity to sort of understand the why behind that. And so a theory can never become a law because they're answering different questions. Nevertheless, both of them are, to the best of our knowledge, the best that we can explain phenomenon in nature at this point in time. Moreover, neither a theory nor a law has ever, not even once, failed any single test that has been presented to it. And trust me, lots of scientists want to shoot down your hypothesis. They want to, independently test it and see if you know what you're talking about. So both theories and laws have been through the ringer. As long as scientists are using the terms properly, then you can rest assured that these are pretty factual descriptions of nature. Now, what happens if a theory or a law needs revision? Usually it's just tweaking something or making it more applicable to more situations. For example, Kepler, as we're going to find out, came up with a third planetary law which talked about the orbits of the planets here in the solar system, but it couldn't really be used in other solar systems or to describe other orbiting bodies because it relied upon proportionalities. And so once Newton came up with his laws, his law of gravity, he was able to tweak Kepler's third law and make it applicable anywhere in the universe, and that's why it's called the universal law of gravity. But nevertheless, Kepler's third law it still holds. It's just limited in what we can apply it to. So it's very rare that a theory or a law is completely overturned and shown to be total bunk. It's usually found to be, oh, well, you were missing this little detail that we can now add, or we can add something else that makes it more applicable in more situations. You see some examples here that are listed. Another example of a law changing is Ampere's law. If you've ever studied electrical circuitry, this has to do with the magnetic field that's generated in an electrical circuit. And Maxwell found that it was only applicable for a steady current, and so if you had a change in current, you needed another term to that law. And so it became the Maxwell-Ampere law once he added that term in. Nevertheless, Ampere's law is still just fine if you're talking about a steady current. It's only if you have a changing current that you need this other term. And so these are some examples of how both theories and laws can change, but again, it's rare to find a theory or law completely invalidated and shown to be totally wrong because, as was shown in the previous slide, it's got to go through all of these tests and never fail a single time. So by the time it gets to the point of being called a theory or a law, it's a pretty good description of nature. Another tool that scientists use is something called a model. We already discussed the model when we talked about the celestial sphere. But usually what this is just a simplified version of something that's actually fairly complex, and it helps us describe what's going on. And so the celestial sphere was a simplified version where we took the distance to the stars out of the equation and just worried about where to point our telescopes. And there are other similar ideas, like the heliocentric model of the solar system is actually a simplification, believe it or not, because you may say, well, wait, don't we all orbit the sun? Isn't that what the heliocentric idea is? And technically that's almost true. The heliocentric model says that the sun is at the center of the solar system and everything orbits it. But in actuality, the sun actually moves in response to the presence of the planets as well. It doesn't sit still at the center, in other words. It actually wobbles a bit and orbits, so to speak, the center of mass of the solar system, which is, still located within the sun itself. So it may seem like I'm splitting hairs here, but this wobble is how we've been able to detect planets that orbit other stars. We've looked for that kind of wobble in other stars. The Bohr model of the atom is a simplification. You may have encountered this if you've taken a chemistry class, but in actuality, we can't know the exact location of electrons. So when we say, oh, they're in this orbital or that orbital, it's really just loosely speaking, we don't know their exact position. So again, a model is simplified, but it helps us understand things and usually describes things pretty well, good enough for most approximations. I skipped through that slide really quick because it was saying that this was a bonus, and it's really not. It's important information here that's in your textbook. So we're going to go back to this idea of history again and how people came to understand things. So at first I kind of set the stage for you by telling you about ancient peoples and what they did to reason through and figure things out about distant objects. And then I've given you, okay, well, this is what science is. Now I'm going to highlight in the Enlightenment era when astronomy really came into its own in being a truly scientific field. How did that take place? Because, you may already know that back in Aristotle's day or Aristarchus's day, there was still a lot of conjecture. There wasn't a whole lot of solid evidence that you could rely upon, and there was a lot of still reliance on this idea of astrology where things in the sky influenced your life. And so how do we go from that to an actual scientific field? So let's start that story with a man called Tycho Brahe. Tycho Brahe was an interesting fellow that was very boisterous and was known to have a golden nose because he lost it in a duel. And he had a lavish observatory that the king of his kingdom bestowed upon him, where he would throw great parties and have a lot of merrymaking. But despite what sounds just like someone who likes to party, he actually had very accurate measurements of the positions of the planets. And what's really remarkable is that he made those measurements without a telescope. He used nothing but his naked eye and some instruments that looked similar to what's being depicted here in the cartoon, where he was able to really get a handle on the positions of the planets throughout time, and was able to measure them within 1 minute of arc. And what that means is, so in a degree, when we were talking about angular size and angular distance, in a degree there are 60 minutes. So he could tell the positions of the planets to an accuracy of 1/60th of a degree, which is really fascinating when you think about it. So with these really precise measurements, no one else had measurements like this. And there was a man named Johannes Kepler who wanted to get a hold of Tycho Brahe's data and try and figure out the nature of which how did the planets orbit the sun. So he took Brahe's data. Incidentally, he got a hold of this data right before Brahe died, because Brahe, in all of his merrymaking, ended up dying of a kidney infection. So in any case, on his deathbed, I believe, as the story goes, that he gave Kepler his data, and Kepler analyzed it. He was a mathematician, and so he was also a very spiritual man who believed that the circle was a divine shape, and that in the heavens it would be the case that planets orbited the sun in perfect circles. However, with this really accurate data of Tycho Brahe's, he was unable to fit the data to the equation for a circle. And so at this point, Kepler faced a dilemma. Do I fudge the data? Do I ignore the data? Do I, revisit my hypothesis? And so, given his choices, it was hard for him to give up on this idea of a perfect circle, yet he suspended this personal feeling and was able to say, okay, let's try out an ellipse, which is an oval shape. And he found that the data fit the equation for an ellipse perfectly for all the planets. And so he came up with his first law. Kepler's first law was that the planets orbit the sun in an ellipse. To get to this point, Kepler really had to embrace the idea of the scientific method, let go of his preconceived notions, revisit his hypothesis, and use the data as the test for whether or not that hypothesis was true, and if not, it needed to be revised, and he revised it to reflect the accuracy of the data. So an ellipse means that we have really an oval shape rather than a perfect circle, and for most of the planets, for most of the planets in our solar system, it's so close to a circle that by eye you probably wouldn't even be able to tell that it's actually an oval in shape. So this cartoon that's drawn here is exaggerating that just so that you can see it. But in this model of an elliptical orbit or an oval-shaped orbit, then the sun is a little bit off-center. It's located in one of what is called two focuses or foci of the ellipse. And so that's Kepler's first law, that the planets orbit the sun in an ellipse with the sun located at one focus. Kepler's second law is that, it's always confusingly worded, that planets sweep out equal areas in equal time. I find that a little bit confusing, but let's take a look at the cartoon and maybe I can explain it a little bit better. On the left-hand side of the cartoon, you see a planet that's being depicted going from point A to point B over a period of 2 months. Okay, so that's maybe a snapshot in time of 2 months of its orbit. On the right-hand side of that, you see a different 2 months being depicted. And if you imagine connecting the dots here and imagining how much of a triangle or angle that amounts to, you see that the one on the left-hand side sort of looks short and fat, where the one on the right-hand side looks long and skinny. But the Kepler second law says, even though they look different shapes, that the amount of area within those is the same. In other words, imagine it being a pizza. You've got a short fat piece or a long skinny piece, but you've got the same amount of pizza either way. And if that's the case, then you can see that in order to produce that fatter piece of pizza, the fatter, shorter piece of pizza, I guess the planet was moving faster, right? Because it moved further in its position on that orbit. So, it had to be moving faster then than when it was making that skinny piece where it's moving kind of slow. If that's both 2 months, you see that arc is much smaller on the right-hand side than on the left-hand side. So basically, when you're closer to the sun, you're going to be moving faster than when you're farther away. And really, the reason behind that has to do with, the force of gravity is stronger there. But of course, Kepler didn't know about the force of gravity. Nonetheless, this law is still true. Okay, and Kepler's third law I mentioned before, that how Newton was able to tweak this once he came up with his universal law of gravity. But basically, Kepler's third law related the distance a planet is on average from the sun to how long it takes to go around its orbit. For the Earth, it's really simple, right? You're going to put in a number on the left-hand side of this equation that's in years, and on the right-hand side, you'll get how far it is in AU. So for the Earth, it's really easy. How long does it take us to go around the sun? 1 year. 1 squared is 1 times 1, which is 1. And so that 1 is equal to the distance cubed. Well, what's the cube root of 1? Well, it's still 1 because we're 1 AU away. So for the Earth, it's very simple. But, you can put in different numbers here. Let's say that there was a planet that was 2 AU away. Then, well, maybe that's a bad example. But, you could put in different numbers and find out different things. Because the thing is that astronomers knew how long different planets took to orbit the sun. But they didn't really know how far away they were. So based upon your observation of how long it would take for that planet to go around, then you could get a handle on how far it must be away. Okay, and no summary of the history of the Enlightenment era as it applies to astronomy would be complete without mentioning Galileo. In Galileo, the common misconception about him is that he invented the telescope. Well, no, he didn't really invent the telescope. The telescope was an instrument that was already, had already been invented, but usually it was used for navigating purposes on the open seas, to see where a distant ship was or whether you were close to land. But Galileo took and built his own telescope that he could turn towards the sky instead. And using the telescope this way, he saw a number of things which at the time were thought to be heretical or blasphemous, and eventually he was put on house arrest and forced to recant all of these claims, even though he had evidence to support them. And it wasn't until hundreds of years later that he was vindicated. But in any case, some of the things that he saw that were what ruffled feathers were the following. So he noticed that the sun was not a perfect sphere. It was thought in those times that it should be perfect, but it actually wasn't. It had spots on it, sunspots. The moon, he saw the craters on the moon. He also noted that there were moons of Jupiter that orbited Jupiter, so not everything was revolving around us or revolving around the sun. He saw the rings of Saturn, but probably didn't really know what they were. They just kind of looked like ears to him. His telescope was not really that powerful, but he could see that there was something there. And probably most importantly, he observed that Venus exhibited phases similar to the moon. And this could only be the case if the planets orbited the sun. You see in the cartoon that if the planets did not orbit the sun and they orbited the way that people thought, then Venus would not show phases. It would always look like the same amount was illuminated to us. But if Venus orbited the sun and was interior to our orbit, then we would see phases the way it's being depicted here. We would see different amounts of Venus being illuminated, which is what Galileo saw. Okay, so with this, we've completed some of the historical overview, and I will see you next lecture. Thank you.